All right, let's look at partial derivatives. All right, let's say you have a function of two variables, z equals f of x comma y. All right, so we want to, you remember that the derivative tells you about the slope of a tangent line, right, or the slope of a curve. All right, z equals f of x comma y is, if you sketch the graph of it, it's going to form a surface in three-dimensional space. All right, then we can still talk about slopes, but you have to specify a direction, right? Because depending on which direction you travel on the surface, the slope will be different. So we can talk about slope in the x direction and the slope in the y direction, right? So let's find the slope of the surface in the x direction. So this is called the partial derivative with respect to x. So we say partial derivative, so this is the notation, partial derivative z with respect to x, or a function name is f, so you can do partial of f with respect to x. Here's a kind of a lazy notation. Instead of using the partial symbol, we can put the subscript x. So this is understood to be a partial derivative with respect to x. All right, so the definition is quite similar to the regular derivative. So you have a limit as h approaches 0, right? Then you have a f of, since we're doing the with respect to x, we only mess with the x component. So you have x plus h, comma y, minus f of x, comma y, all over h, right? So you're basically holding y constant, then you take the derivative with respect to x. Right. On the other hand, if you want to do the slope in the y direction, you're going to take the partial derivative with respect to y, and the notation is as usual. And then you have a limit as h approaches 0. So since in this case we're messing, so we're holding x constant, then we are doing the derivative with respect to y. So you have a f of x comma y plus h minus f of x comma y all over h. All right. Since we know how to take the derivative, only difference is we're holding the other constant, holding other variable constant, but the way you take the derivative is pretty much the same. All right, so let's look at this example. All right, you have a function f of x comma y is equal to e to the x times y cubed, right? So if you want to do a partial derivative with respect to x, we're pretending that the y is just going to be a number. So y is a number, right? So if you take the derivative, so here y cubed is a number, so I'll just put that there. And then we take the derivative of e to the x, which happens to be e to the x, right? So partial derivatives is actually exactly the same as the original function. And if you want to evaluate the partial derivative f at a natural log of 2, 3, so you plug in natural log 2 for x and the 3 for y. So you have e to the, then you plug in natural log of 2, and then you plug in 3 and then cubed, right? So this is going to be equal to, so 3 cubed is 27, and e and a natural log cancel out because they are inverses of each other. So essentially you're just going to get 2. So 2 times 27 is 54. Right? All right, let's look at the partial derivative with respect to y. All right? Now I'm holding x as constant. So you have e to the x is just a number, so I'll just put the e to the x, right? But when you take the derivative of y cubed, it's going to be 3y squared. So we're going to put the 3 here and the y squared, right? So you're just holding x constant, and you just take the derivative as usual with respect to y, right? So if you plug in x equals natural log 2, y equals 3, you get 3 times e to the natural log of 2 and multiply by 3 squared, right? So this is going to be, actually, this is going to be 54 again, because 3 squared is 9, 9 times 3 is 27, and then multiply by 2. So it's going to be 54 again, right? But anyway, the way you take the derivative, the partial derivative is exactly the same as before. Only thing you have to worry about is making sure that you're holding the other variable constant. Then you just take the derivative as usual. All right, that's it. I hope that this was clear.